Very good evening, sir. Very good evening to everyone. Welcome to today's second session on reviving quantumness, two instances of repowering protocol by Dr. H.S. Karthik, sir. We'll be shortly starting the session. Sir, meanwhile, you can try to share your presentation if it is there, so that we will test it.
Okay. Hello all.
Yes.
Am I audible?
Yes, sir. Yes, sir. Audible.
Okay, cool, great. So I will share.
Yes, sir.
So you have to allow me to share.
Just a minute, sir. See, sir, now are you able to?
Okay, yes. It is taking some time.
Yes, sir. Yes, sir. If it's Mac, it will take some time.
I had.
It's Windows?
No, it's Mac.
It's Mac.
It's an iPad.
Yes, yes.
Okay, the screen.
Yes, sir.
Is the screen?
Yes, sir. Yes, I can see.
Okay.
Yes, sir.
Okay.
Just a couple of minutes, sir. We'll wait for a few more participants.
Sure, sure.
Ramesh sir will join and
yeah,
start.
Sure.
Yes.
Most of them are from Karnataka, right?
Yes, sir. Majority of the participants are from Karnataka.
So I
But
can
from
use
that, Tamil Nadu,
okay.
Andhra
So
Pradesh,
all right. Okay.
Madhya Pradesh, and Maharashtra and UP.
Okay.
Karnataka is major, sir.
Yeah.
Next.
So I thought I will also use a mix of Kannada and speak, but it is okay.
Dr. Karthik, good afternoon and welcome. Karthik ji, namaskara.
Good afternoon, sir. Namaskara.
Welcome to India.
Yeah, thank you. Is it seen? Is my screen seen?
Just a moment, I will introduce, then you can speak. Okay. Today we have with us the eminent speaker, Dr. H.S. Karthik. He will be speaking on reviving quantumness, instances of repowering protocol. Let me give a brief introduction of his achievement. Dr. H.S. Karthik has completed his PhD from a very prestigious Raman Research Institute, Bangalore. After graduating, he was a visiting research fellow at the University of Geneva in Switzerland. Upon returning to India, he held a position as a postdoctoral fellow for a brief period of time at the Institute of Mathematical Sciences, Chennai. At present, he pursues his postdoctoral research work at the International Center for Theory of Quantum Technologies, University of He works on topics related to quantum correlations and quantum communications, metrology, and on aspects related to time in quantumness theory. He will be speaking on, as I told, on reviving quantumness, two instances of repowering protocols. We will introduce some of the quantum foundational notions, paradoxes, which have helped to shape the paradigm of quantum information science, the importance of studying aspects of quantum theories to recognize the apparency of the violations of these paradoxes of information processing applications and communication protocols. Some elegant examples of communication protocols will also be discussed, and instances of reviving quantumness in this talk. With this brief introduction, I once again welcome Dr. H.S. Karthik, who has just landed yesterday in Bangalore. Despite of his busy schedule, he has been very kind enough. In fact, he is one of the members of our quantum technology expert group. This I once again welcome him, and also I welcome all the participants to this webinar on behalf of KSTA. And now over to you, Dr. Karthik, for your presentation.
Thank you very much, Dr. Ramesh. In fact, Professor Ramesh. It's part of KSTA. First as a student, as now as contributing to it. Back in, so I should tell about myself a little bit extra, that I was a student at Bangalore University, and KSTA had also at the time arranged such webinars on topics related to basic and fundamental research. And it was during that time that I got acquainted with this association. And in fact, I had, as a student, also bagged their famed prize, for the quiz context. So it is nice to be contributing now to KSTA, so that students like me, who are, I hear that they are among a good group at present now in this webinar, will also get to some extent a little bit aware of awareness. And is my screen, sorry, is my screen seen? Is my screen? I am sharing it.
No, sir, not it.
Because it just
was earlier. It was earlier.
Because it just closed now.
Okay.
So let me share it once again.
Try to reshare, yes, sir.
Kindly let me know if the screen sharing stops. Okay.
Yes, sir. Yes, sir. I will inform you, sir.
So am I audible at least?
Yes, sir. Yes, sir. It's audible.
At least let me continue saying that, okay,
Yes,
as at least as students, you will have a very good opportunity for having this kind of an ecosystem where researchers like me and also experienced researchers like how yesterday you had Professor Usha speak on various aspects of current and then also continuing trends in our field of quantum information science, and now which has ramifications in technology. So the importance is, as far as, I mean, when I was a student and also now that I am on the other side of the line, I realized that it is not that one gets to know or one has to know everything a presenter presents. It is the ecosystem. Okay, it is the awareness. It is just being there. That's quite important. So I hope you will enjoy what I am going to present. I will be as far as possible a little bit chatty and also at the same time casual. So this is not something which is, I want you to carry the essence of the talk rather than the details, because the details, I have mentioned several references. You can go back to the video and you can see up to the details, write to me, everything is fine. Okay, so this is the most important part. Get the essence, get what is it that researchers like me and other experienced researchers now are doing, so that you will get an idea of what it is, and then you carry forward whatever you are interested in towards. Okay, so I will start. Okay, it's still taking some time. Additionally, I will try to address almost all the questions, but if I am unable to, you can write to me. I will provide you my email address. You can write to me and then ask any relevant and appropriate questions. Okay, so it is taking a good amount of time.
I think it's PPT is with heavy images and videos, I think, sir.
There is no video in that.
No, at least images.
Yeah.
If you have PDF, that will take very little time, I think, sir.
Okay, so shall I will convert it and then get back. Okay, just give me 1 minute.
Okay, sir, no issues.
Because it says that I am sharing the screen. So see now?
Yes, sir. Yes, sir. Now we
Okay.
got it. Now we got it.
Okay, so
Yes.
Yes, now visible.
Please go ahead. Please go.
okay. Okay, so okay, somebody's Audio is on. Okay. So let me start. So this is, I come from international, I'm a part of a postdoc. I'm doing currently a postdoc at the International Center for Theory of Quantum Technologies, ICTQT, which is a part of University of Gdańsk, Poland. And it's a fantastic place to be at. So if there are PhD students or postdocs, please keep a note that there will be positions which will be advertised. So there is a vibrant group of diverse areas and also people, fantastic people whom you can meet, interact, and also have a fruitful collaborative research. So please feel free to check ICTQT, and then keep in mind if you want to apply, please do so. So today I'll be talking on quantumness basically, and the broad outline is this. I'll give you, because I did get to know from Professor Ramesh that there will be a lot of students who will be joining in across places. So I will keep it as brief as possible. So the pace will be that I will try to give as much details or fundamentals as possible. And if needed, I will pick up the pace in some places and at the same time dwell a little bit more on some things which is, really nice and cool. And at the same time, allow you to follow some things. It's okay if you don't follow much of it, the details. Okay. So the pace is like mixed. So the first instance of quantumness is to observe enhanced violation of some indicators, quantumness indicators. And the second one is in what are called as quantum random access codes, on which I work now, and to see how they can be made to resist noise, And the other part is, with all these things, what are the implications to other foundational aspects? And then I will give a strong takeaway message and then okay. So this is the introduction to quantumness. Now, there are theorists and experimentalists. So how do I, for example, I'm a theorist. So how do I think? I think from the point of view of this way. It is in terms of schematic, okay? Whereas an experimentalist will obviously think in this way. So mine is this. Of course, I am also now trying to look into this aspect as well. So how can there be a talk on quantum and no Feynman mentioned in it, So this is one of the most used quotations. So I will also use it, but this is as you delve deeper and deeper into quantum mechanics or quantum theory, do research on it, this makes even more sense. So what I'm going to tell you about is what I'm right now currently telling you. It is my task to convince you not to turn away because you don't understand it, because I don't understand it, and I'm sure that nobody does. So now let me introduce some of the other basic. So let me start with some of the really basic stuff. So I will rush through some of the parts of it. So the basic aspect of quantum theory is the representation of a quantum state, which is psi. It is an abstract entity and it belongs to what is called as a Hilbert space. And this is a complete vector space, which is equipped with what is called as an inner product. Okay. So what is meant by completeness? So these are the technicalities which are the keywords which you should also take it into account, and then go back and then search into to satisfy your own curiosity. So if there is a quantum state, so that can, because it's a part of the Hilbert space, so it can be expanded in terms of these basic states. And these basic states have to have the properties that they are orthogonal somebody's so these basis states are orthogonal, and at the same time they have this property called as completeness. So this you can think of it as vectors in a three-dimensional space. Like you have the x unit vector, y unit vector, and z unit vector. So they are orthogonal and they are complete in the sense that any given vector can be expressed in terms of these basis states. Okay, and these CIs, they are the complex coefficients. So then you have the evolution equation given in terms of the famed Schrodinger's equation, which is a first order time derivative, and then it has the Hamiltonian. And if you have a representation in terms of position and momentum, it takes up the second order derivative in either x or p. And then this is the evolution equation, that the psi of t is a unitary which acts on the psi at an earlier time. So this is the unitary operator. And the state of a system is that I showed you earlier that the psi can be expanded in terms of the basis state. So one of the basis states, so they are called as pure. And then we introduce another representation of the state of a system, which is in terms of what is called as rho, and that is the density matrix, written in this form. So this is the ket, and this is the bra. So this is the Dirac-Ket-Bra notation, and this is an expansion in terms of it. So the idea is this, that this density matrix takes into consideration both of the pure as well as mixedness. So what is meant by the pure representation of a state? Imagine, so now I'll keep some technical terms. So now as I go, I introduce some other basic stuff like the single spin half particle. So I'm sure you're aware of all those things. So a spin half is the most fundamental quantum object, and it has two levels, right? Two levels to it. So now if, let us say, if you throw a fair coin and then if it heads, and then you can represent it in terms of you can associate it with 0. In case of tails, you can represent or associate that with the ket vector 1. So how do we capture this situation of the probabilities of throwing probabilities of getting heads or tail in terms of representing it as a state? So is it captured by this? So that is not possible. The state is not represented by what is called as a state vector, but by what is called as a density operator. So this is basically the difference now between this pure and then this kind of. So it allows us to have a single representation, because you can have a row written it as phi I, or in terms of a complete. So either it can have a single entity or it can have a series of entities. So this encapsulates both the representations of pure as well as mixedness. So the mixedness in this case is given by, so a classical, so in a fair coin can be represented in terms of a density operator via this way. It doesn't have what are called as the interference terms. Okay, or the, so because this is a, in terms of a representation, it is a 2x2 matrix with half half, and then here 0 and here 0. So these two terms are 0, and they do not and are not present when you represent the toss of a coin in terms of a density operator. So the measurement, what is meant by a projective measurement? A projective measurement is also the case that it is represented by pi, and it has these properties that this is always greater or equal to 0. So that means it's a semi-definite positive operator, and it is always, it has because it's so in the language it's called as, okay, it has it singles out a definite value, and the fact that, and two value. So the thing is, two orthogonal projectors, the overlap of it is 0. So this is the meaning of it. And then it is always complete. That means when you perform a projective measurement, it's going to throw some value at least. So this is the representation in terms of, so notice that this, if you write it, it is the same thing as a pure state. So the mathematical representation is almost the same, but the idea is that this is a projective. It can be considered as a projection onto a particular pure state. So the measurement probability is that this performing on a given state rho of this particular project I will give you a probability. And this is the probability that psi can be projected onto an eigenstate phi I with giving the eigenvalue I. So this is basically what you know as Bond's rule. And then last but not the least, this is the expectation value to calculate it. So we are going, so this is all the quantum mechanics which we are going to need. And you need to think a lot, because we can do a lot of things with only this much amount of quantum mechanics which is needed as of now. And last but not the least, this is the famed wave function collapse. That is, if you take a projective measurement, the state from psi will collapse, will pick out a particular value, p phi, with the probability of a given. Okay. So this is the famed notion that how is it that you don't get one particular value, but a series of particular values with the associated probability. So this is the notion of what is called as a wave function collapse. So this is the fundamental departing point of quantum with the classical notion of ideas. So now with this, I'll come to the quintessential starting point of any talk on quantum information, which is basically EPR, because even if it is not possible to grasp everything, I urge all of you to read the paper, because this is one of the fantastic and clearly written papers out there. So this was my starting point of research. So I will also encourage your budding student, so please at least give it a read once. So I will. So now, because I started with EPR, I'll give you why is it that they started with the EPR argument. Because in classical mechanics or classical theory, the idea was already very solid. So because there is a definite aim that given any configuration representation of a state, or a configuration space representation of a state, the program of classical mechanics is very simple. That is, given some initial conditions, you need to find out what is the next ensuing condition, next ensuing values of the initial x and p, which corresponds to as representing a state or a configuration representation of a state for any classical system of particles or even a single entity. So if it starts with an initial values, so you can predict with arbitrary precision x of t and p of t via either the Hamilton's equations of motion or the Euler-Lagrange or even simply the Newtonian equations of motion. So the idea and the dynamics, I mean, the notion or the aim of the dynamics is pretty clear. However, it is in the arbitrary precision with which we can provide the x of t naught and the p of t naught, which is fundamentally different in quantum mechanics. And this was what gave Einstein and his collaborators a nudge to write and ask fundamental questions, which showed and which gave way to write the EPR paper. So for any success, for the success of any physical theory, they asked, there are two questions. Is the theory correct or is theory complete? And it is the second question that EPR tries to consider as applied to quantum theory. So every element of physical reality must have a counterpart in the physical theory. So this is one of the necessary conditions for any complete theory, because they are focusing only on the complete theory. And criteria for reality is that if without in any way disturbing any system, we can predict with certainty of a value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. So that means if I am making a measurement of position X, and if I get the value of the position without disturbing the system, so that means that it corresponds to an element of physical reality for that particular system. And every element of the physical reality must have a counterpart in this physical theory. So that means the position value should have a valid representation in the physical theory. So these are the two criterions. And to give a simple example, so they asked if there are two physical observables represented by these A and B, and if these are, okay, there is an equal to sign here. So if they are having this kind of an eigenvalue, sorry,
sir, there is some disturbance from other screen. You please continue, sir.
yeah, okay. So there are two observables, and these two physical entities, which are represented as operators in the theory, if they do not commute, so that means they do not have a simultaneous set of eigenstates which can represent the realities of those two operators. And as a result of which, this suggests that this leaves us with two possibilities. That is, quantum theory is incomplete, or quantum theory is fine, but no simultaneous realities for these two non-commuting operators. So to give the example, let's take the Bohm's version of this EPR paradox. So that means there are two spin half particles, A and B. So they have the spin sigma A and then sigma B. So the A represents for the A and B for the B part of the spin. So let's measure sigma Z at A's end. So now let's suppose that these two spin half particles share what is called as a perfectly anticorrelated. The spins are so perfectly anticorrelated, okay? Like in the form of what is called as a singlet state. So let's measure sigma Z at A's end. Let's measure sigma X at A's end, okay? So if you do so, because of this perfect anticorrelation property, at B's end, even without measurement, you get the idea of the values of sigma Z as well as sigma X without even measuring it. So that means you have the idea of what could be the spin values even at B's end, even without measuring it, and at the same time, because they are because they are I'm sorry, there is a lot of disturbance.
Sorry, sir. We have moved them to lobby.
So the spin operators, even though they do not commute, they seem to have definite values at B's end. So this is the EPR paradox. So that means they concluded that they could predict the values of measurements at B's end, even though they do not commute. So that means there are hidden realities at B's end, which quantum theory or the wave function doesn't account to. So therefore, they concluded saying that quantum theory is an incomplete description of reality, and there must be a way to extend it so that such hidden realities could be accounted for. And that is what is called as the hidden variable theory. So can this spooky action at a distance? Because if you make a measurement at A, you can get to know the value of B, or it can also be that the state of B could inevitably be disturbed even though you're not making any measurement at B. Okay, so this is all in counterfactual way of argumenting about the EPR. So can the spooky action at a distance predictions of quantum mechanics be replaced by some sort of local, statistical, and also classically understandable way? And that's what is called as the hidden variable theory. And Bell's famous contribution to it, and which we are all enjoying right now, about the ramifications of EPR's as well as Bell's contribution towards such foundational aspects is encapsulated by his famed work, and that implied or that showed that it's not possible to have that there doesn't exist any hidden variable theory which can explain the quantum mechanical properties of what are called as entangled states. So he cites that the physical predictions of quantum theory disagree with those of any local hidden variable theory. And this is his famous paper. As I suggested, for any student, please go through the paper once again. Even if you don't understand, read it and keep getting it back to it. So it's just the essence that you need to catch. So what is local realism, which Bell proposed? Realism is a worldview according to which external reality is assumed to exist and have definite properties, whether we are observing or not. The second thing is the locality. That means the measurements made at, let us say, at a place. Let me usually take, so there are Alice and Bob. So Alice is at a spatially separated position from Bob. So measurements made at Alice's end should not influence the result obtained at Bob's end. So this is basically encapsulated into form of what is called as locality. These are, even though these are English terms, they have very strong mathematical representations. As I told you, take the essence and then go back to the references for more details. So the joint assumption of local realism is encapsulated both in terms of what is called as a convex sum of product structure for the individual probabilities. So here A is the outcome and small a is the setting, and B is the outcome and small b is the setting. Okay. So then these are averaged over lambda. So realism is that the probability is either 1 or 0. Okay, that means there exist definite realities. And locality is the fact that the outcome of A only depends on the setting at A, but not on B. Okay. So this is the idea of locality. So both these things put together is the notion of local realism, and this restricts correlations in the form of what is called as Bell's inequality, which is this. And quantum mechanical, for any quantum mechanical state, which is what is called as entangled, they violate Bell's inequality beyond the value 2. So this, and the algebraic maximum of what, so there can be certain other correlations where this correlations, which has a maximum value of, which has a bound on either plus or minus 1. So if you take the maximum correlations of 1, 1, 1, and if this entity becomes minus 1, so they can go up to the value 4. And there are certain other what are called as no signaling set of correlations, which are called as PR box correlations, which can go to 4. But in nature, we are yet to find such sort of correlations. So this is okay. So this is Schrodinger's quote saying that quantum entanglement is the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. Okay. So there is this very nice set of resonance articles by Professor Chaturvedi, Mukunda, and Simon, and also there is a very good review on quantum entanglement by the famous Hrodesky group, who are there in my present University of Gdańsk. Very good set of basic articles, and also which right now can also form as a foundational basis for any student entering into quantum information theory. So please go through both of them. And the idea is that So this is how Simon and Mukunda and Professor Chaturvedi says about EPR, and also about Einstein's and his collaborators, that one is left with the feeling that EPR's criticism reduces to their not liking quantum mechanics, as it does not agree with their prejudices about any theory. So it's about their prejudice is what they comment on. And the quantum entanglement review says that the so-called paradoxes of quantum theory right now are nothing but can be reversed and then looked at as some sort of a platform for spurring interdisciplinary research, and also for looking at these as the test beds on which new technological improvisations of quantum information science can be achieved. So these early foundational conflicts or paradoxes of quantum theory, they paved way to new leaps of precision measurements. That's what they say, and which in fact is creating or has created this area of quantum information science. Okay, so identity. I think again the screen.
We lost, sir. Yes, sir. Screen sharing stopped.
Okay, so I will I get more time in case I have to need it? Because it is from 3:30 to what, 4:45, and I'm losing time on these things. So so is the screen in now? Okay.
Yes, sir. Yes, sir. Visible, sir. Now you can continue.
So let me go now quickly to other aspects of it. So till now I spoke on two spatially separated systems, but then address the quantumness, how to observe the quantumness of two separated systems, and then non-classicality of two separated quantum systems. So right now, let's ask the question about single systems. So how and when do physical systems stop to behave quantum mechanically and then begin to behave classically? How do we address these kind of questions? How do we even put across the idea of characterizing the non-classicality transition precisely in terms of how Bell did for two spatially separated quantum correlated systems? So, is it possible to see superpositions for a single system having, let us say, n levels to it, is the question which we pose now. So in other words, it is addressing the non-classicality of a single quantum system. So for that, Leggett and Garg in 85 proposed what is called as macrorealism, which has some sort of a similar structure, but in the form of address to single systems. So this is based on macrorealism per se and non-invasive measurability. So that means a given single macroscopic system can exist indefinite, and it has physical properties which have definite values independent of the act of observation. And the second part is the non-invasive measurability. That means the measurement of a physical observable on a single system at any instant of time should not influence or should not disturb the subsequent evolution of the system. These two things can be put across as what is called as the Leggett-Garg inequality, which is some sort of a temporal, can be understood as a temporal Bell inequality. So that means to take a single system and then you pick a physical observable having a dichotomic values, that means the values is plus or minus 1, and then keep making measurements at times intervals, let's say delta t. So if the temporal correlation, so the value of it is plus 1 or minus 1 or 0. So that means it can have It can have perfect correlation or perfect anti-correlation, or it can have no correlation at all. So now there are Legit
Sir, we lost the presentation, sir, again. Sorry.
I don't know. Is this happening?
Sir, I have a question. Thanks for the nice presentation. Sir, what exactly is quantum entanglement? Is it
Before
because
before asking question, please introduce yourself, please. I request all the audience to introduce yourself before asking the question.
Yeah.
Introduce yourself before asking.
sir, I'm Dr. Shantala.
Yeah.
I'm
Hello.
Dr. Shantala, Associate
Hello.
Professor in Physics Department at Oxford College of Engineering. Actually, we teach this quantum computing for these students. What exactly is quantum entanglement? Is it due
Okay.
to the thing?
So I will take some of these questions at the end, if you don't mind, because I mean, because I'm losing time with
Okay, sir. Okay, thanks.
other. So I will take all the questions. Don't worry. I will take all the questions and then I will respond to you.
Okay.
So right now I am focusing on characterizing the non-classicality of how to address the non-classicality of a single system, not of two systems where entanglement plays in. So this is for a single system. So that means you make measurements at time t1, t2, t3 of a single variable. Let's say a spin measurement at time t1, t2, t3, and then you collect the correlations. So because these are dichotomic in nature, so they can have either perfect correlation or anti-correlation or no correlation at all. So the value of the correlation is between -1 and +1. So if you plug into that, you get a 3-term, what is called as a Legit-Garg inequality, which is with this. And the maximum value of it is +1 and then -3. So macro realism, that means taking into consideration these two postulates, which seem reasonable enough for any macroscopic systems to behave in our so-called common day-to-day world, they have this Legit-Garg correlation or inequality between +1 and -3. Whereas a quantum mechanical system, let's say a spin-half particle, if you start with the initial state as I/2 and then take the Hamiltonian for evolution as this, and then you pick the observable as sigma z, then make measurements on it, and then calculate these C12, C23, and C13. So that will, you can see that this is the violation. Okay, so there is a violation of Legit-Garg inequality, which indicates non-macro realistic or what is called as quantum behavior. Okay, so this is the macro realistic domain, but you can see that quantum mechanics violates this way. Okay, so that means either one of the two postulates must be failing, or that violation of LGI is a tool for showing quantumness in the macroscopic domain. So all macro realistic theories obey LGI, whereas quantum theory does not. So Professor Mahesh at ICTQT Pune's group was one among the first people to do this experiment in an NMR system. So this is a very nicely written article also, so please go through it. And this is the experimental proof saying that, okay, or verification saying that you do have a violation here for a single spin half. And there are reviews on this, Legit-Garg inequalities and all. I have not gone through the technicalities of what is meant by verifying how is it that they do these sort of fundamental tests in an experiment, because they need to have, because quantum measurements are primarily invasive, that means they disturb the states of the system. So one has to concoct what is called as ideal non-negative set of measurements. So that means, so these are the technicalities which I leave as of now, but you can take a look into those articles. So let me run through these parts now. So this is the background of characterizing non-classicalities or quantumness for two separate systems, spatially separated systems in terms of what is called as entanglement and then violation of Bell's inequality. And for the single system, you can have a characterization of the non-classicality in terms of what is called as LG, Leggett-Garg inequality, checking Leggett-Garg inequality violations. Okay, for two separate systems, it's Bell, and for a single system, it is Leggett-Garg. So now I bring in to discuss about what is it that I did. Okay, so it's stopped sharing once again.
Yes, sir.
Yeah, I don't know. So, but this is going to keep eating time, so I don't know. So I will request 50 minutes more, if you don't mind.
Yes, sir. Fine, sir. No worries.
Yeah, thank you. So macro realism bounds on three-term LGI, and the maximum value a quantum mechanical system can violate up to from a two-level system is 3 by 2, which is 1.5. This is the maximum value. Like how Bell's inequality gets maximally violated up to 2√2. So for the three-term LGI, it is 1.5. And then the algebraic maximum bound is 3. Okay. I told you that for the spatially separated non-classical correlations, you cannot only quantum theory doesn't allow you to go beyond 2√2, whereas PR box correlations can go up to 4. Whereas in the case of for a single system, you can go up to algebraic maximum value of 3. And this was recently shown by Budroni and then Emery in their 2014 paper, wherein they exploited what is called as state update rules, which is nothing, which corresponds to preserving, which corresponds to utilizing measurements which preserve degeneracy when you have more than two-level systems. So when you have more than two-level systems, you can have, because the values are plus or minus 1, so you can either preserve degeneracy or you can break the degeneracies. So if you have certain set of measurement update rules which preserve degeneracy, then you do not go beyond 3 by 2 for any n-level system. Whereas if you have degeneracy breaking, what are called as one Neumann set of measurements, then you can go beyond 3 by 2 for a three-term LGI and then go up to an algebraic maximum of 3 as the system dimension tends to infinity. So this is what they showed. And in other experiments also showed experimentally that for a three-level system, you can go beyond 1.5 and up to 1.757. So this was reported in this paper by Hemant Katia and all. So what we did right now was, so whatever I did, I will just run through now, okay? So what we did was to show that being a qubit being a quintessentially fundamental quantum system can also show violation of LGI up to 3. And you don't need to have the idea, you don't need, you can witness the violation up to the algebraic maximum 3, and that you don't have to go for the case of the n-level system is what. So contrasting to their paper, which showed that even a qubit it's possible for it to show a maximum violation of 3, but the price is that it needs a special sort of an evolution. And this is what is called as the PT symmetric evolution. So PT symmetric evolution is basically that any given Hermitian given Hamiltonian is basically Hermitian, right? So in quantum mechanics, all the operators, whatever we are involved are basically Hermitian. Okay, that's because the eigenvalues of the Hermitian operators are real. However, there are certain specific set of operators which have this symmetry, extra symmetry, which is called as the PT, parity time reversal symmetry. So one of such special Hamiltonian has a very peculiar feature that this is non-Hermitian, yet it possesses real eigenvalues. Okay, so that means to say that this Hamiltonian commutes with this parity time reversal symmetry. That means it is a parity time symmetric effective evolution, effective Hamiltonian, which, if acted on a system, can and it which can be used to act on a particular two-level system. So this is one aspect. The other aspect is that these have, though they are non-Hermitian, they have eigenvalues which are real, and these are two eigenvectors of the Hamiltonian, which are basically not orthogonal, but it depends on what are called as the metric orthogonal. So I will not go into the details. The idea is, so the most important part is that this is the value alpha. So if you notice, if alpha is 0, this is base, and if you take S as 1, so if alpha is 0, it's basically sigma x. Okay, so the Hamiltonian is just basically sigma x. Whereas if you take alpha going from 0 to pi over 2, so the eigenvalues and then the eigenvectors. So for when alpha is pi over 2, the eigenvalues go to 0, and then the eigenvectors become what is called as they coalesce. Okay, so that means they become one, not two separate things, but they just become one. So there is just only one value. Okay, so the alpha is equal to pi over 2 is basically what's called as the exceptional point. So now what did we do? What we did was to take this PT symmetric Hamiltonian, you construct an evolution operator, and then you evolve it. Okay, so the idea is this. So you take a single system, you evolve it with this PT symmetric Hamiltonian evolution, which is characterized by this non-hermiticity factor called alpha, and you make a measurement. And once again, you evolve it, and then you make a measurement, and then collect the correlation. Okay, this correlation, you can see that this violates LGI up to 3. Okay, and this goes to 3 as alpha tends to pi over 2. So this is where even the PT symmetry also breaks. So this is a symmetry breaking point. So this can also be viewed as some sort of a signature where you can see that if you are considering a PT symmetric system, so that is where, so this is like an indicator that, okay, there is a breaking point of the symmetry. So here, there's no dynamical symmetry, but there is an eigenvalue transition between real and then complex. Because it's a non-Hermitian Hamiltonian, it only till the symmetry holds, the eigenvalues are real, after which they become complex. So there is an eigenvalue transition. So that's the transition part. And you can notice that this is very much similar to what they did. And the nature of the curve is also the same thing. So that means you have a single system, you can mimic or you can simulate a n-level system by having what is called as a PT symmetric dynamics tool. So recently, there were 3 other groups, one in China. I mean, all of them more or less on China, but one is also in USA, which have adapted our result into performing experiments on 3 different platforms. Okay, so these are the 3 references which they have done on. So now let me go through very, very quickly about what is called as till now you have looked at correlations with respect to time, and for the bell, it was the correlation with respect to spatial sense. What I'm going to do now is to characterize non-classicality of a single system once again, but from a very different route. Okay, and this is what is called as a prepare and measure scenario. Whereas in the case of the Leggettger, it involved measurements across 2 times, okay? So this is the fundamental difference. So here in the case of a prepare and measure scenario, there is this Alice's lab, which has a setting X. It's like a button, and then you press it, and then out comes a state which encodes that X. And then here there is Bob's lab, on which there is a machine, and then there is a button Y on it. You press it, and then out comes a value B. Okay. So this is what is called as a preparation, because you prepared the system and then sent it to Bob, who is at a spatially different distant location, and then he does this pressing of Y, and then he gets the outcome B, and this is what is called as the measurement. So there is a preparation, and then there is a measurement. Okay, so this is the schematic which I'm going to use, and this is also the framework on which I am going to introduce to you another non-classicality indicator, just like Leggett-Gerg, but here it will be a different indicator for a single system. And this kind of a scenario has a use in the form of what is called as a protocol, which is called a quantum random access code. So the idea of a quantum random access code, or basically random access codes or classical random access codes, is the following. Let's suppose that you meet somebody in a conference and you talk to some people, and then you go back to your place. And after some years, you will have a chance meeting upon one of the persons whom you had met in the conference. And he will say like, hey, did you meet, do you remember some X person? Let's say Professor Ramesh, let's say. And then you will be wondering like, okay, now you have to access that particular part of memory in your system, or I mean like in your brain, which only has the information about identifying Professor Ramesh. Okay, so that means this person whom you met just asked you as a very specific question, like, do you remember Professor Ramesh whom you met in the conference? So you only have to retrieve that part of access which is related to identifying all the information about Professor Ramesh. So that means you should get imagery. So this is for the random access memory point, but here it is with respect to a communication. So that means it's a random access code. So that means there are two, let us say, in the form of a communication game. So there are 2 bits, A0 and A1. Both can take value between 0 and 1. And then these 2, you encode it into a quantum system, and then Alice encodes it and then sends it to Bob. And then she will say, okay, what do you know? What is the value of A0? So then he will perform some measurement and then retrieve. So the outcome. So Bob will retrieve the value of this A0 using his outcome. So this is basically what is called as a random access code. Okay, so this is a communication game. So classically, what is the best strategy? So that means there are 4 possibilities. So one of the best possible strategy is to send only the first bit always. Okay, so if that is the case, so then Bob will have a probability of recovering the first bit. If Alice asks the first bit, then he can easily access it with so the probability of accessing 0 or so then he will have a accessing probability of half. And then in the case if because she's always sending the first bit, so the probability of 0 or 1 is just half. So it is half times always for sure that he can access. And then the other part is you have the half. So if she asks about A1, so he doesn't know, so he basically guesses. So that means half of the times. So then this is just nothing but 3 or 4 times. So the probability of him winning the game, okay, on an average is 3/4. Okay. However, so this is when you send, and it sends only a bit, okay, a bit of message. However, if she sends a qubit, okay, if she sends a qubit, so then you can have scenarios where you can beat the success probability of Bob, which was possible only with a bit. So that means I'll give you an instance by an example. So let's suppose that you have the row 00 by a state, row 01 by another state, row 10 and row 11 in this way. And then, so these are the states which Alice encodes the 00, 01, 10, and 11, and then sends it to Bob. So what does Bob do? He has to decode it, right? So that means if she asks, so then he has two possible measurements. The two possible measurements. So if she asks, okay, what is the first value? So that means he performs this measurement and then gets a value. If she asks, what is this? The second one, so then she performs this value. So on an average, the success probability is going to be 0.85, which is greater than 3/4, which is 0.75. So sending a qubit, so that means you are compressing more information in terms of a qubit, and then you send it, so that the decoding will also happen via a quantum measurement, and then you can retrieve the success probability or the average success probability of Bob in retrieving the bit value which was sought by Alice is fundamentally more, and and this is the quantum advantage, of having a bit of communication. So that means classical communication to a quantum communication. So the original idea was given by Stephen Weissner in his famous paper, but it was like forgotten. It was like, okay, it's there, but then these guys, Ambani's Wazirani, Ashim Naik, and Ashama, they reintroduced it in this. They recognized and then reintroduced it in this journal, in this paper. And then there are a lot of work which has ensued on. So I mentioned only some of these things. And this is the paper which is, let's say, I'm now going to base further on. And then this also has aspects towards randomness expansion. And there are also entanglement assisted version of it as well. So now let's go quickly to the other aspect, which I told you that it has. So using a prepare and measure scenario, you can have a characterization of non-classicality for single systems. Different. And this is the arena of what is called as dimension weaknesses. So the standard protocol of a quantum random access code is, as I told you, is an example of a prepare and measure scenario. And the warrant of security in these kind of communication scenarios lies under the purview of what is called a semi-device independent quantum key distribution, that is SDI. And what is meant by semi-device independence is the fact that these preparations, whatever Alice prepares, for example, I showed you very specific characterizations of preparations here. So these, in the semi-device independent scenario, you don't have to have that. So that means when Alice is producing these kind of states, it's not necessary to know what are the exact preparations. And those are the freedom which you have in the form of what is called a semi-device independent. Now, once you have this, but at least in order to address the non-classicality aspect, what is the so-called, say, for example, in this case, I told you that it is a quantum system which is going across. So that how do I certify that it is indeed quantum? Okay. In order to do that, we introduce what is called they introduced what is called as the semi-device independent arena, and the impositions or the restrictions is that I don't need to know the exact preparations, but that these single systems will have a cap on the dimension of the Hilbert space of the system being prepared and then sent across. So that means the dimension of the system is bounded from above. Okay. So this is the analogy. So which I'm going to show between a random access code and then the dimension witness. An example of which is the following. So consider two systems which are of dimension 2. Okay. So Alice produces and so she encodes these 2 bits and then sends it across in the form of the system. And then so the dimension of this is just 2. So that is all that is known of this particular thing which is going across. So remember that a bit of communication also has dimension 2, and then a qubit also has a dimension 2. Okay, so if Alice is sending across this system to Bob, it can as well be a bit or a qubit. So the idea is to know or to differentiate what is being sent across by performing measurements at Bob's end. Okay, and you can notice that the probability of him obtaining some results at his end, that is probability of B given AY. What is A? A is nothing but A0 into A1. Okay, so probability of these A0 B given these bits and then the value Y of the setting is that it's given by the trace of the state and then the measurement what he performs. Okay, so with this one can introduce what is called as a dimension witness, which is basically a linear inequality comprising of these certain probabilities which I mentioned here. Okay, so one of an example for, let us say, if for 0, 0, 0, 1, 1, 0, and then 1, 1. So these are the 4 basic preparations corresponding to that. So if we restrict it to 4 preparations, just like in this case, and then if we restrict to measurements as 2, which corresponds to M as Y equals 0, and then M as Y is equal to 1. So then this is the dimension witness which you can. What is this E? That is 0, 0. It's nothing but this things. Okay. So once you have that, the dimension witness for a D is equal to 2 system is bounded by 2. Okay. Now notice that the success probability or the average success probability of a random access code is given by this. And this can be related to the dimension witness via this form. So that means if there is a system, if there is a qubit which or a bit which is going across, this has a maximum value of 2. And as a result, this average, the optimal or the average success probability corresponds to 3/4. Whereas if it is a qubit, this term will go up to 2√2, and then you can get the value of 0.85. Okay, for a qubit. So this is how the notion of or the security or the idea of characterizing what the non-classicality of a system which is being sent from Alice to Bob can be captured via calculating or computing this dimension witness. Okay, and this is related to the average success probability of a random access code. As such, for the case for the D is equal to 2 case, either I talk of dimension witness or a average success probability of Bob, both are one and the same. Okay. So now I will quickly rush through what I did with what I'm presently doing, or rather what we did right now, and then we're going to extend it, is to consider such scenarios when you have noise along the channel between Alice and Bob. So that means you have degradation of the system due to noise. So quickly running through, any unitary transformation of a density matrix can be written in this way, but whereas a general quantum channel includes what is because of the fact that this system interacts with an environment with a joint unitary. So this can be contrasted, or this can be captured via what is called as a channel, a general quantum channel. And this is the form of it. So here, when there is only unitary interaction, so there is no noise. So this is the transformation of the system. Whereas here, if the system interacts with an environment, this is how the evolution happens. Okay, the representation of the system evolving happens in this way. So that means you take the system, plug it with the environment, evolve joint unitarily, and then you trace out. That means you leave out, you take away the environment part of it. So the ensuing or the resulting evolution is in this way, where these EIs are what are called as cross operators, and these can be seen. I mean, you for further reading, I will refer you to Nielsen and Chuang, which is a basic fundamental book on quantum information. So running through, so now you all might have heard of what is called as spontaneous emission. So that is modeled as what is called as amplitude damping channel. Okay, so the representation, a mathematical representation of what is called as a spontaneous emission is given via these cross operators in this way. Okay, and this is the noise. The gamma here captures the strength of the noise. Okay, so this represents a decay of population from the excited state to the ground state, and E1 and E2 will represent such decay of from the excited state to the ground state. And then if it's already in the ground state, so that means these operators will not affect anything on that. So now let's go back to the quantum. So now what I'm considering is the scenario of a quantum random access code where Alice encodes all these states or these bits in the form of these states, and then sends it across a channel which is noisy, which has this specific amplitude damping noise. Okay, and then the measurements done by Bob for decoding, if she asks either the first bit or the second bit, is this. Once you have that, what we did was to have what are called as noise adapting schemes. In other words, even despite, so that means when you have noise along the channel, the quantumness of the system which is being transferred across gets degraded. And how do I check that? I will check either the success probability of random access code or the dimension witness. So that means the dimension witness stops violating. Before, when there was no noise, it was violating up to 2√2, which was greater than 2. But now it will start decreasing because of the fact that there is presence of noise. What we did was to overcome such noise by proposing or by adopting what are called as these filters. So that means we employ such operations or such schemes, and then show that despite the presence of noise along the channel, we can still have a way to indicate the non-classic or revive the non-classicality of a particular quantum system. So this is what is called as noise adaptation technique or noise reviving, noise resilient techniques. So these operations are given this way. And then, so therefore, once you have that, the parameters here, F, okay, you can notice that when F is 0, it is just identity. And when F is just 1, it is nothing but 0 or 1. Okay, so there is two particular cases or range of values for F is between 0 and 1. So the average success probability of Bob in that case will translate to include both the strength of noise as well as the strength of the filters. Okay. And there is a there is an experiment which was recently done at the University of Concepcion in Chile, South America, wherein they implemented this scheme, and you can notice that here is Alice, which is like this, okay? And the channel here is the amplitude damping channel, which is basically this part, which is this. And here is Bob, who includes this. So the operations here, including these putting of these plates, they are nothing but this FA and then FB. Okay. So how do these sort of pictures, or how does the 4 states here get transformed into, I mean, how is it that when I write mathematically, they are represented via this way, but how do I see them in terms of an actual experiment is via the following. So here is the laser which goes through a crystal and then gets 2 entangled photons. One of them goes this way and the other one goes via this way. And then, so let's consider only this part. Okay, so this part is not considered as of now. So this is the only part. Let's consider this. So it goes, and then here is the preparation. There is a theta A, which picks out these 4 particular preparations. Okay, and then once after that, it goes through this field, this FA set of glass plates, and then it goes through an amplitude damping channel, and then it goes through. So this is where the spatial separation happens, okay, along the fiber optic cables here. So these FBs are in Bob's station, and he applies it before performing measurements. So this theta B are like the measurements here. Okay. So choosing, so these are the halfway plates. So if you choose the angles there, then you can correspond here to 4 preparations and appropriately here to 2 measurements. Once you have that, so then you detect it via D1 and then D2, and then you take this photon and then how is it that they check all these sorry, probabilities is in terms of what is called as coincidence detection. Okay. So this is the idea. So how is the cross operators? How is the amplitude damping channel implemented? Sorry. So that is, I will explain in the last part of my talk in this way. So here is the PBS, that is the polarizing beam splitter. So the photon, whatever comes out here, has gone through the 4 preparations, and then this set of filters, and then now is entering. So let's call the state which is entering as psi, okay, and which is clubbed along with the 0th state of the mode. So now, so there are these parts which is either 0 or then 1. I hope you can see it. Once you have, so the action of this polarizing beam splitter is given in this way, where this H is picking out the horizontal polarization, and then V translates to picking out the vertical polarization. Okay. Okay. V. So once you have that, then you can see that there are 2 modes here which separates out as 0 and then 1. So horizontal will go into this part, and then the V part goes into the other one. Okay. So once you have that, then this state transforms into this way. And then after that, you can see that the H, okay, you maybe Okay, I can zoom in. Can you see?
Yes, sir. Yes, sir.
Yeah. So you can see that the H theta 1 here is there only along the one part, okay? Along the dotted one. So once you have that, so the H theta 1 acts only along the one part and then peaks out. So nothing on there is on 0. And then in the return leg, again the PBS, they will go and then come back again to PBS, the action of which is represented in this way. And then finally, what you get is the state here, and which is written in this way. And you can see that this is already in the form of the cross operation, which I showed here. Okay, so, and this is how you recognize K0 and then K1 in terms of the halfway plate, what you have. And finally, what we did in the form of a result is that you have on the left-hand side, I mean, on the y-axis, the witness, the dimension witness, which earlier I had represented it as sigma. So in this case, it is written as W. And here is the success probability of average success probability of Bob. And here along is the axis is along the noise, along the which is there in the amplitude damping channel. Okay. So F corresponds to the amount of filtering or the amount of extra operations, this what we or the scheme what we have employed here. So the F corresponds to what is called as the filtering operations, and they are the ones which give this effect of noise robusting this whole protocol. So when F is 0, you get a critical value of gamma C. So that means it stops violating the dimension witness. So that means I wouldn't know whether the system transforming across is a quantum or a classical system, or in other words, I lose the quantum advantage. Okay. And this is also the case that, okay, it crosses the 0.75 part. Now, when I increase the value of F to 0.45 or to 0.9, so that means I am making it noise tolerant by this much. When it is 0.9, so this is noise tolerant up to this much. So I am increasing the noise tolerance by employing such schemes. So this is a recent article which will be going up in a few days. So this is the part of the work which I did along with the team in Chile. And I have a last part of it, which shows that, look, these sort of non-classicality kind of related ideas or capturing the essence of non-classicality in terms of indicators like the dimension witness or the Leggett-Garg inequalities, or for two systems in terms of Bell or CHSH inequalities, is that these are very much important tools, and they have ramifications towards certain application in terms of ensuring security in communication scenarios, just like how I explained right now for the case of quantum random access code. With developments, technology related aspects will be pushed forward. However, it's quite important to realize and at the same time make sure that advancing technology should be in turn applied to foundational ideas so that future technological applications even can be expanded beyond what is possible today and can also lead to a better and a clear control over such technological revolutions. With this, I end my preliminary version of what I did and what I did. So all that is needed right now is for you, for the students, is to, if you have any questions, go. I mean, feel free to ask, and at the same time, also be aware of the fact that even if you have not understood many things, whatever I told you, just having that awareness, I hope that it will propel you towards learning some things which in the future days will be more easily accessible, and which you can, if you're interested, can also implement it, given the push for technology, quantum technology from both our Karnataka government via this KST initiative, and also via the national quantum missions, which are happening across India. Thank you very much.
Dr. Karthik, thank you very much for a very scholarly and informative talk on reviving quantumness, two instances of repowering protocols. You explained it very well, so that even a degree student and non-physicist could also understand easily. I am sure many of the students and teaching faculty would certainly benefited by your talk. On behalf of KST and all the participants, thank you very much. Now, the session is open for discussions. If you have any questions, please ask Dr. Karthik, who is an international expert. I'm sure you will be highly benefited if you can have question answer Q&A session. You can ask a few questions and clear your doubts. It will be good. Over to all the participants.
Hello.
Yeah, please.
Yeah, I am Sai Kumar. Can you hear me, sir?
Yeah,
yes.
Yes. Thanks for the talk, sir. I have two questions. I'm from Chennai, and we are also working on Leggettgard inequalities in the context of fermionic systems. One doubt which I am having, the first doubt I am having is, as far as this Leggettgard inequality is concerned, all we can say is when there is a violation, it might be due to this macro realism, or it might be due to this correlation between the different measurements at different instants of time. So will it be of like any advantage or fundamental interest if we can narrow down in our system whatever we are considering, out of these two, what is the actual reason for the violation? In the sense, if we can pinpoint that the violation is not due to this quantum coherence or the superposition, and it is due to the correlation between the measurements which is made at different instants of time. So that is my first question. And my second question is, as far as these PT symmetric Hamiltonians are concerned, the general doubt is in quantum communication systems, is it possible to realize these PT symmetric Hamiltonians? Because whatever I read is, like, theoretically these PT symmetric Hamiltonians, what I read is they have advantage of arresting decoherence. The coherence time is increased very to a large extent, but experimentally, is it possible to incorporate these PT symmetric effects in quantum communications? Thank you, sir.
Okay, hi, first of all, hi, Sai Kumar. So thank you for your questions. Regarding the first question, yes, these are the things which even me, when I was a budding student, I was asking questions like these things. I mean, the idea is very, very, even though the question is very, very simple, it's really hard to pinpoint such things, because these are questions which need proper formulations, and at the same time have different avenues towards proposing experiments, how to address these kind of aspects. So one of the ways, as I mentioned, was via considering what are called as ideal negative result measurements. So that means when you perform a measurement, you're going to disturb the system. So you are going to get a value. So the idea is not to consider that value, but to consider what you didn't get. Okay, so that is the ideal negative result measurement. So once you have that, then you are in principle implementing what is called as the non-invasiveness. Okay, so this is one aspect of ensuring that you have that when you're testing for the Legedgarg, what's actually happening in the Legedgarg case. So this is one sort of a way to ensure that you are indeed not, the violation is not due to the fact, okay, due to your measurement scheme. So this is one thing. So there are other ways which I do recall that there was this one paper by Weissman et al., which looked at alternate ways to derive this Legedgarg inequality. Okay, that is to include what is called as the signal locality and also the include what is called as the deterministic point of view. So they give a alternate derivation, though the content is the same, but the alternate derivation. So there one can have, I mean, they claim that, I mean, they say that they can have a way to address this aspect. This is also true with respect to the spatial scenario. However, the idea is that there you can have real-time implementations of what is called as the no signaling scenarios. Okay, so you can ensure that the signal, whatever goes across when you make a measurement in terms of when are you going to make a measurement? So that means you will use a random number generator to do that. So you can time those things, and then you can ensure that the timing falls across different scenarios. Okay, so I mean, I had one slide. I mean, I had the extended part of the talk where I would have spoken about these aspects, but because of the lack of time, I didn't. So this has got to do with like drawing space-time diagrams and then ensuring that, okay, when you make a measurement at Alice's end, the measurement at Bob's end is spatially separate. So in terms of the space-time diagrams, you can see that, okay, they are spatially separated and then not belonging to the case that they are, you know, in the causal past of Alice's measurements or the Bob's measurements. Okay, so this is one aspect. But in the case of Legedgarg, this is the thing. And pertaining to your second question with respect to PT symmetry, yes, indeed, such systems. It is like, you know, the thing of PT symmetry is very peculiar because it was already a quantum phenomena. It arose due to quantum phenomena, and now it's like after some years it is like homecoming because there are, due to the advent of technology, now there can be certain systems where such dynamics of PT symmetry can be seen. All right, and has already been implemented, where, as I showed you, there are three particular instances of systems or platforms of systems where such Legedgarg violations have been done on PT symmetric systems, okay, wherein you can have this PT symmetry in implementation. So I hope the second, I mean, I have answered both the parts. If not, you please feel free to write to me. I can provide you some references so that it helps you.
Like, thank you, sir. Like, I will try to send you a mail where I ask it more elaborate.
Yeah, sure.
Thank you. Thank you.
Thank you, sir. Thank you, sir. There is one question. It was pending in the last session. I would like to ask here today, sir. So since you are the right person to answer for this, what is the relationship between quantum no-clone theorem and quantum state discrimination?
Okay, so so the idea is that in the case of Okay, this will also be addressed. I mean, the no cloning theorem will also be addressed by Dr. Akshata in tomorrow's talk. But let me just tell you in very brief and very simple terms that no cloning theorem is attributed to the fact that, okay, you have two unknown states and it gives you, it tells you that you can't clone you can't clone an unknown state. Okay. For example, in a copy admission, in a classical copy admission, you have a Xerox, so you go take a Xerox and then come back. So this is just copy. Whereas in the case of a quantum state, if you do not know, let us say if you have the state represented as alpha 0 plus beta 1, if you don't know alpha and beta there, you cannot clone so that means there are no unitary operations which allow you to clone an unknown state. So unknown is the fact that you don't know what this alpha and beta is. Okay, you can definitely clone if you have a non-unitary operation, but you can't clone it using unitary operations. So this is the aspect. The second part refers to quantum discrimination. Quantum discrimination, as the name itself refers, it means that you have to discriminate two states. Okay, so now what's the relation between them is that you have, let us say that you have a noisy cloning, just like how I explained. Okay, so you have a system and then there is a noisy way that you can clone it. So that means after this process of cloning, you get two noisy versions of the original one. So these two, how close are they? How do, I mean, because if you say they're the clones, that one is the clone of the other, so that means you should be able to, you should not be able to discriminate it, correct? So however, because there is a noisy version here, so there is a relation between how much amount of noisy cloning you can have, and then how much amount of noise can be tolerated with respect to the cloning, and what is the value of how much amount of discrimination can I do for these two noisy clones. So that is the idea that imperfect cloning of these two states is always possible, but only up to a certain value of this discrimination. And this discrimination has a name, one of the names, it's fidelity. And this, there are certain papers by Professor Dagmar Bruce and Hillary et al., which I can share later, that they say that you can only do so with an optimal fidelity of 5/6. Okay. And what is meant by perfect cloning? So that means if there is perfect cloning, that means the fidelity is 1. So here, so you can only have noisy cloning up to 5/6. That's the value. So this is the relation. And for more so, you can, you can read some of the reviews also. And at the same time, I can also forward some of the references. Thank you.
Thank you, sir. Thank you, sir. If any other questions, please ask. The participants can ask them.
Hello. There are any questions? Please. Doctor, there is one question.
Oh, yeah. Actually, I remembered
Yeah.
one Dr. Shamala asked about quantum entanglement. What is quantum entanglement?
Yeah. Hello.
Okay.
Dr. Shamala, are you there? Okay, she must have left.
Yeah.
Doctor, how does the repowering protocol work to restore quantum properties in a system that has lost its quantumness?
So that is exactly the idea of the talk, which, I mean, the gist of the talk which I gave right now. So even if you have a possibility that you are going to lose the quantumness of a system, we provide a scheme. We have provided a scheme, and there are other schemes as well which can revive the quantumness.
Thank you very much.
Yeah.
Yeah, if there are no questions, Umesh?
No, sir, there are no questions, sir.
Okay. Doctor, thank you very much for a very, very informative and scholarly talk. I'm sure many students and teaching faculty would have broadened their horizon of this particular new emerging field of quantum science and technology. On behalf of KSTA and all the participants, thank you very much. Tomorrow we'll be having a talk by Dr. Akshata Shanai. She is a senior scientist in the International Center for Theory of Quantum Technology, University of Gdańsk, Poland. She will be speaking on quantum cryptography. This is also an very important talk by an international expert. I request all the participants to join by 3:25 so that we can start the session exactly at 3:30. Please don't miss this series of webinars. This is just a sensitization kind of webinars. We'll be having application and higher level advanced talks a little bit later, maybe in September we'll be having. We'll have both webinars and also offline meetings to make students and teaching faculty understand what is quantum mechanics and what research they could take up as a student or as a faculty. These talks and webinars will be of use. I request all of you to join by 3:25. At this juncture, I also thank senior people who have joined this webinar, right from Dr. K.V. Rao, Director of Pilikula Regional Science Center. Now we have with us Dr. Sudha Madam, who is also an expert committee member. Then Dr. Akshata will be giving a talk tomorrow. Dr. Anant Naik, who is also a member of the expert committee of KSTA Quantum Science and Technology. And we have with us Dr. Yashoda, Dr. Girija, Dr. Sangeeta, Dr. Mano Maharajan, and Sai Kumar and others. I thank all of you for joining this webinar. I'm sure this talk is of a great use for your future research. Thank you very much.
Thank you. Thank you very much. Bye. Thank you, sir.
Thank you, sir. Thank you, one and all.
Yeah.